So we want to prove an important result in this lecture. So the result we want to prove is this. Say G is a subgroup of automorphisms of E, and corresponding to G there is a fixed field, this EG, which we will denote by F. Then dimension of E over F is say n, then this n is also equal to the size of the group. So say your group consists of elements phi 1, which is just the identity map, then phi 2, phi 3 all the way to phi n. So there are n elements here. So these n elements form a group, and they are subgroup of automorphisms of E over F. So you can see there are n elements here. So this is the n which comes here. So the proof is by contradiction. So first we will say that let the basis E over F is m, and say this n here is greater than E over F, which is m. So E over F equals to m means that there are some basis elements, say b1, b2, b3, b4 all the way to bm. These are the basis elements of vector space E over F. So this m is this number of basis elements right here. So we are saying that n here, which is the size of the group, is greater than E over F. So n, which is the size of the group, phi 1 to phi n, is greater than E over F. And we want a contradiction. So we want a contradiction. So consider the following system of equations. So you have phi 1 acting on b1 x1, phi 2 acting on b1 x2, phi n acting on b1 xn. Then again you will have phi 1 acting on b2. So here in this entire row you have everything acting on b1. The second row you will have everything acting on b2, and so on. And in the last row you have phi 1 acting on bm x1, phi 2 acting on bm x2, and then phi n acting on bm xn. So b1, b2 all the way to bm. So there are m equations here. So m equations, and x1, x2, x3 all the way to xn, there are n unknowns. So you have n unknowns and you have m equations. So we have m equations corresponding to b1, b2, b3 all the way to bm, and you have n unknowns which is corresponding to x1, x2 all the way to xn. Now we are given that n is greater than m. So this is what we have assumed, n is greater than m. So therefore we will have some non-trivial solutions to these equations. Solution for x1, x2 all the way to xn. So say the solution is s1, s2 all the way to sn, and they could lie in F, and therefore they will also lie in E. Now you pick some elements a1, a2 all the way to am in F. So you pick some elements here. So these are fixed by phi I, which I could be any of these phi's here. I could be 1, 2, 3, whatever. So this phi I lies in G. So this phi I is an element of G, and G is a subgroup of automorphisms of E over F. So these phi i's therefore fix all these elements. So what we do is we multiply these elements, all these elements, into this equation right here. So multiply these elements. So you take a1 and you multiply with the first equation, take a2, multiply with the second, and the last equation you multiply am with. Now you have multiplied a1 throughout here. So you have a1 times here, you have a1 here, and you have a1 here. But this phi is fixed. It does not change a1. This phi 2 does not change a1. This phi 1 does not change a1. So you can take a1 inside. So you take a1 here inside, a1 inside, a1 inside. So for the second equation you multiply with a2. So you have a2 b2 here, a2 b2 here, a2 b2 here. So corresponding you will have again have phi 1, but inside you will have a2 b2 s1, and so on. And here in the last equation you will have multiply by am. So you have multiply am here, you multiply with am here, multiply with am here. So am will get inside. You have am bm s1, phi 2 am bm all the way to phi n am bm. So these are the equations you get. Now you start adding. So you add all these elements together. So this phi1 comes out and you have s1 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 right here. This comes here, and inside you have a1 b1 all the way to am bm. Similarly, phi2 s2 you will have a1 to am bm inside, and phi n again you have phi n and sn sn. You take them out here and here, and inside you have a1 b1 a2 b2 all the way to am bm. So notice that how do elements of this field E look like? So elements of E look like this. So they are vector space with basis this, and say there are some elements a1 a2 am, so they will look like this: a1 b1 plus a2 b2 all the way to am bm. I would say this is equal to some alpha. So instead of all these, you put alpha here, you put alpha here, so you get phi1 alpha s1 phi n alpha sn. So all these are the same element alpha right here. So all these are the same element alpha, and we put them in here. So once you put these elements in here, you have alpha as in E. So this shows linear dependence of phi I over E. So this you can clearly see. So you have linear dependence of phi I over E, because this equation is non-trivial. And this contradicts the corollary we had in the previous lecture. The previous lecture was linear independence of group characters. So recall that if we have distinct automorphisms of E, then they are linearly independent as function on E. So this was just a corollary. So you can see in the previous lecture we said, you have this character of a group is a homomorphism from G to F star, and if you have such a character, then the distinct characters chi1 chi2 all the way to chi n are linearly independent. So this G you replace with E star, this F star you also replace with E star. So E star is a multiplicative group, and the only thing missing here is 0, so 0 maps to 0. So now you can see this phi I lies in the automorphisms of E, and instead of chi1 chi2 all the way to chi n being linearly independent, we are saying phi1 phi2 all the way to phi n are linearly independent. These are linearly independent. So this was our corollary, but here we are getting a contradiction, because we are getting this nonlinear relationship, so which shows that they are not linearly independent. So we have a contradiction right here. Therefore we can say that n is less than equal to E over F. So we have already shown that n is less than equal to this degree of extension. So to show that only equality holds, we have to show that this less than would lead to contradiction. So notice that n is again the size of our group, where this phi1 is just identity map. So let n less than be the degree of extension. So then we can choose at least n plus 1 linearly independent elements of E, because this n is less than the degree of extension, and say you have chosen these elements b1 b2 all the way to bn plus 1, and then you form a system of equations. So you form a system of equations in n plus 1 unknowns. So x1 x2 all the way to xn plus 1, these are n plus 1 unknowns. So x1 x2 all the way to xn plus 1, and you have equations corresponding to these phis. So the first equation corresponds to phi1, second equation would correspond to phi2. Notice this is phi1 b1 x1, again phi1 b2 x2, phi1 bn plus 1 xn plus 1. So this equation corresponds to all phi1s, second equation corresponds to phi2, third equation corresponds to phi3, and so on, and this nth equation corresponds to phi n. So you have n equations here. So we have n equations and n plus 1 unknowns. So n equations and n plus 1 unknowns, and therefore we will have some non-trivial solutions. So some of these solutions are not all 0. So say your solution set is s1 to sn plus 1. So you solve for x1, you get s1, solve for x2, you get s2, and so on. Now, important remark here is, this is very important, at least one of them is not an element of F. So see, all these solutions s1, s2, all the way to Sn plus 1, they obviously lie in this E, and some of them could also lie in F, but there is at least one which does not lie in F. Now this is because this phi1 is just the identity map. So this phi1 is just the identity map. So if you actually look through this equation carefully, this equation is nothing but, say, if you put the solution set, so x1 we've solved as s1, so this becomes b1 s1 plus this becomes b2 s2 all the way to bn plus 1 sn plus 1 equals to 0. So notice that this phi1 is identity map right here. So you have this equation, so you get this equation, and that would mean that this is a linearly dependent system if this is these b's are and s's are non-trivial. So we have said that we have non-trivial solutions s1 to sn plus 1. These are non-trivial, and we took non-trivial elements b1 to bn plus 1. So that means this is a linearly dependent system. But we said we have a linearly independent system of elements on E. So it has to be the case that out of these s's, one of them does not lie in F, because otherwise over F, if all of them lie in F, then over F this becomes a linearly dependent system. So at least one of them would not lie. So we will pick some elements, say we pick s1, renumber them, pick s1 which does not lie in F. So we are going to remember this later, that s1 does not lie in F. So because this phi1 is just the identity map, and this would violate the linear independence of elements b1 to bn plus 1. So not all these solutions are 0, 0, but some of them could be 0. So we now choose non-zero solutions, s1 to sr, and this r is minimal. So we choose non-zero solutions such that this r is minimal. Out of all solutions, you choose the minimal number of non-zero solutions. So r is minimal. So our contradiction is that we will contradict this. So we will do something to get set of solutions which is less than r later on, which will give a contradiction. So this is where the contradiction is going to arise. Now if you have a solution set, since this is all a linear equation, so you had a solution set like this, then you can divide by one of these solutions. And if you divide throughout by one of these solutions, you will still have a solution set, because you can divide both sides. This side is anywhere 0, and you can divide by one of the solutions, and you will still have a solution. So say you divide throughout by one of the elements sr, and then you get a solution set s1 to sr minus 1 comma 1. So basically what s1 we are rewriting for s1 divided by sr, and s2 we are writing by as s2 over sr. S3 is nothing but S3 over SR, and so on. So we are just renaming them here, and SR over SR is just 1. So we have divided by one of our solutions. As you can see, just dividing by one of the solutions will not change it. So if you divide this entire thing by Sn plus 1, this will become 1, and this becomes S2 divided by Sn plus 1. This becomes S1 divided by Sn plus 1. So you have not changed the solution, you still have the same solution. Like you have a solution basically. So we have this new solution set. Now we plug this into this equation right here. So you plug this solution set into this equation, and others are just 0, because we are taking, because some of the solutions could be 0. What we are taking is the minimal number of non-zero solutions. We are taking the minimal number of non-zero solutions. So these equations corresponding to non-zero just become phi1 b1. Instead of x1 you have s1 sr minus 1, and then you have sr here. So phi1 br sr, but sr is just 1 here because you have divided sr by sr. So this is just 1. So these equations become these equations after you plug in. For x1 you plug in s1, for x2 s2, for xr minus 1 sr minus 1, and for xr you have 1, and for the rest of the terms you plug in 0 0 0. So this system reduces to this system, and we have already said that, say, one of the elements S1 is not in F. Now this S1 is not in F. That means this group G, so this group G, this is a subgroup of automorphisms of E and fixed field F. So this group G is going to fix this field F, but S1 is not in F. So there should be some automorphism in group G which will permute S1. So say this phi j is some special automorphism which will permute S1. So that is phi j of S1 is not equal to S1 because S1 does not lie in the field F. So now you apply this permutation to this set of equations above here. So we are just putting phi j here. So phi j phi 1 b1, and then phi j here, phi j of S1, then phi j phi 1 br minus 1, phi j sr minus 1, phi j phi 1. Just putting phi j everywhere. Again phi j here, b1, then phi j of S1. So just putting phi j here and then phi j here, phi j sr minus 1, and then 0 here. So notice that this phi j also lies in this group. This phi j lies within this group. So if you multiply every element by phi j, what you're going to get is again the same group G, because this group G is closed, it is finite, and multiplying by phi j is just permuting the elements of the group. So you still get the group G, but the things get permuted. So for example, say this phi j phi n, say this gets permuted to some phi 3. So it could get permuted to anything. I'm just writing phi 3 here for concreteness. So then this gets permuted to phi 3. So then you have phi 3 b1, and then everything else comes the same, phi j s1. So again this gets permuted to phi 3. Everything else remains the same. Just copy it down, phi j sr minus 1, and this also gets copied to phi 3. So we will subtract this equation from the corresponding equation phi 3 here. So say you had a phi 3 equation here, which was phi 3, everything else remains the same, b1 s1, then you have phi 3 br minus 1 sr minus 1 plus phi 3 br equals to 0. So now you can see the trick. If I subtract, so this equation is there, from this equation we subtract this equation. So if you subtract from this equation, you can immediately see this will cancel out with this, and what we will get is, so first term would look like this, phi 3 b1, this is the same in both the terms. So this is same here, this is same here. So phi 3 b1 comes out, and what remains inside is this s1 here, s1 minus phi j of s1, and here it will come out to be phi 3 br minus 1, so this remains here, and then from inside you have and this set equals to 0, because anyway phi 3 cancels out. Now this you can do for every such equation, you just need to know where it sends to. So we do this for all the equations. So you see what is phi 1 here, subtract phi 1 here, see what is phi 4 here, subtract phi 4 here, and so on. So you have n equations here, you subtract n equations here, the corresponding ones where you get the elements permuted. So subtracting for I equals to 1 to n, you get this. So instead of 3 I'm writing just I. So phi I b1 s1 minus phi j s1, then phi I br minus 1 sr minus 1 phi j sr minus 1 equals to 0. So instead of just 3, you can have all n phi's. So these 1, 2, 3, 4, all the things, they correspond to phi 1, phi 2, all the way to phi n. Special case of phi 3 we have shown just above. Now notice that this is not 0. Precisely because of this here, because S1 is not in the field, so this is non-zero. So you have at least a non-trivial solution for these n equations. So these are n equations, because you can keep changing I, you will get n equations. X1 is not 0, so you have a non-trivial solution, and this is less than R solutions, because you know your terms only go till R minus 1, since this rth term got cancelled out. So you have only R minus 1. You can see this R minus 1 ends at R minus 1. So this is X1, then you have X2 all the way to this is XR minus 1. So you have less than R solutions. Whereas here we said that R is minimal and you cannot have less than R solutions. So you have a contradiction. So we arrived at a contradiction because we were able to construct less than R solutions. And we initially said that R was the minimal number of these non-zero solutions. So obviously this less than does not work. So we already showed it was less than equal to, and now we are showing that less than is impossible. So the only case remaining is this. There is an equality. So degree of E over F is n, which is also the size of the subgroup of automorphisms which fix field F.